Let's talk about something we all take for granted, something so woven into our daily lives that we barely notice it: the refrigerator. That quiet hum in your kitchen is more than just background noise. It's a pillar of modern life, quietly working around the clock to keep our food safe and our lives running smoothly. Refrigeration keeps our food fresh for days or even weeks, dramatically reducing waste and making it possible to enjoy a variety of foods year-round. It also stores vital medicines like vaccines and insulin, protecting health and saving lives. But this everyday hero comes with a hidden cost, one that's easy to overlook until you see it reflected in your electricity bill or consider its impact on the planet. Our dependence on cooling is massive. It's not just our homes. Supermarkets, hospitals, and even the data centers powering the internet all rely on refrigeration and air conditioning to function. This vast network of cooling units consumes enormous amounts of energy every single day, contributing significantly to global electricity demand and environmental stress. The technology behind refrigeration? It's over a century old. While it's been refined, the basic principles haven't changed much, and now those old methods are starting to show their age. For decades, we've relied on compressing and expanding gases to move heat. But the chemicals used, refrigerants, have often been problematic, both for our health and the environment. Early refrigerants like CFCs damaged the ozone layer, leading to global action to phase them out. Their replacements, while safer for the ozone, are potent greenhouse gases that trap heat in our atmosphere and accelerate climate change. As global temperatures rise and more people seek relief from the heat, demand for cooling is skyrocketing. Sticking with outdated technology simply isn't an option if we want a sustainable future. We need a smarter, cleaner solution, one that meets our needs without sacrificing the health of our planet or future generations. The answer? A revolution in cooling technology. Imagine systems that are not only efficient and safe, but also environmentally friendly. Cooling that works with nature, not against it. Scientists are now turning to a fundamental force of nature, magnetism, to develop new ways to keep things cold, using materials and methods that could transform the industry. Imagine a future where cooling your home or preserving your food doesn't come at the planet's expense, but instead helps build a cleaner, greener world for everyone. The challenge ahead is enormous, but so is the opportunity. With innovation and determination, we can reshape how the world stays cool. It's time to rethink how we keep things cold, to question old assumptions and embrace new possibilities. The next generation of cooling could change everything, from the way we live to the health of our planet. Let's explore how this transformation is already beginning. The journey starts with understanding the problem, recognizing the true cost of our current systems and the urgent need for change. And it ends with a new way to chill, one that's better for us and for the world we share. Have you ever wondered what's really happening inside your refrigerator every time you open the door? It's a marvel of modern engineering that we often take for granted. The secret behind this everyday miracle is something called vapor compression refrigeration, a technology that's been keeping our food fresh for over a century. At the heart of the system is a powerful compressor. This device squeezes a special chemical gas known as a refrigerant, increasing both its pressure and temperature dramatically. The now hot high-pressure gas travels through coils at the back of your fridge, where it releases its heat into your kitchen air. That's why those coils feel warm to the touch. As the gas cools down, it transforms into a liquid, condensing along the way. This liquid is then forced through a tiny expansion valve, where it rapidly evaporates, turning cold almost instantly. The cold vapor now absorbs heat from inside the fridge, pulling warmth out of your food and keeping everything chilled. This cycle repeats over and over, working tirelessly day and night. But there's a hidden cost. The refrigerants used in this process are notorious for their environmental impact. Older refrigerants, like CFCs, were once widely used, but ended up destroying the ozone layer, letting in harmful ultraviolet rays. Their replacements, HFCs, don't harm the ozone, but they're extremely potent greenhouse gases, trapping heat in our atmosphere. When fridges leak or are thrown away carelessly, these gases escape, contributing to global warming and climate change. Ironically, the very systems designed to keep us cool are making the planet hotter, creating a vicious cycle that's hard to break. It's a clever and efficient system, but clearly it's time for a new approach, one that doesn't sacrifice the environment for our comfort. Scientists and engineers around the world are racing to invent eco-friendly cooling solutions that can keep things cold without causing harm. The search for a better, greener way to cool our world is underway. Let's explore what the future might hold. What if we could cool without harmful gases? Enter magnetic refrigeration. This technology uses solid materials and magnetic fields instead of compressors and gases. The science behind it is the magnetocaloric effect. Some materials heat up in a magnetic field and cool down when the field is removed. It's like stretching a rubber band. Energy in, it warms. Release, it cools. The magnetic field aligns the material's internal structure, releasing heat. Remove the field and the structure relaxes, absorbing heat and becoming cold. By cycling this process, you create a continuous cooling loop. No harmful gases, no noisy compressors, just magnets and smart materials. It's elegant, clean, and based on fundamental physics. This could be the future of refrigeration. The potential is huge, but how does it actually work in practice? Let's dive deeper. The magnetocaloric effect is a fascinating phenomenon, but it only works with a select group of special materials that respond dramatically to magnetic fields. Among these, gadolinium stands out as the star performer. This rare earth metal has unique magnetic properties that make it ideal for magnetic cooling applications. What makes gadolinium truly remarkable is its Curie temperature. This is the point where its magnetocaloric effect is strongest, and it happens to be right around room temperature, making it perfect for everyday cooling needs. Here's how the process works. When you apply a magnetic field to gadolinium, its atoms align, causing the metal to heat up almost instantly. To manage this heat, water is pumped over the hot metal, efficiently carrying the heat away and cooling the system. When the magnetic field is removed, gadolinium's atoms return to their original state, and the metal cools rapidly, absorbing heat from its surroundings in the process. The result is chilled water, which can then be used to cool your fridge, air conditioner, or even industrial systems, all without traditional refrigerants. By moving gadolinium in and out of a magnetic field using a rotating wheel, you create a solid-state heat pump. No moving gas, no noisy compressor, just efficient, direct cooling. This technology is not only quieter and more reliable, but it's also potentially more energy efficient than conventional cooling systems. However, there's a catch. Gadolinium is both rare and expensive, which limits its widespread use in commercial products. That's why scientists around the world are searching for better, more affordable materials that can deliver the same or even better performance. If researchers can discover the right material, magnetic cooling could become a mainstream technology, revolutionizing how we keep things cold. The science behind magnetocaloric cooling is solid. The real challenge now is scaling up the technology for everyday use and making it cost-effective. Let's take a closer look at how researchers are pushing the boundaries of what's possible in the world of magnetic cooling. Gadolinium was just the beginning. Scientists at Ames National Laboratory made a breakthrough by mixing gadolinium with silicon and germanium. The result? A new alloy with a magnetocaloric effect twice as strong as pure gadolinium. This material changes its crystal structure when magnetized, releasing even more heat. When the field is removed, it cools dramatically. This discovery opened the door to engineering even better materials. Now, researchers are exploring alloys with common elements like iron and manganese, the goal powerful, affordable, and durable magnetic coolants. The dream of a practical magnetic fridge is closer than ever, but there are still hurdles to overcome. So why aren't magnetic fridges everywhere yet? The main challenges are strong, expensive magnets and the cost of materials. Powerful permanent magnets are heavy and pricey. Magnetocaloric materials must withstand millions of cycles without breaking down. System efficiency and compact design are tough engineering problems. Heat exchangers must be highly efficient. Engineers are experimenting with new designs to solve these issues. It's a race to make magnetic cooling affordable and reliable. Innovation and investment are key to bringing this tech to your kitchen. Despite the challenges, companies are racing to commercialize magnetic refrigeration. General Electric has built working prototypes aiming for efficient, quiet home appliances. In Europe, companies like Cooltech Applications have launched commercial systems for medical and retail use. These early products prove the technology works outside the lab. Niche markets like wine coolers and medical storage are the first adopters. These field tests are crucial for refining the tech and lowering costs. The magnetic fridge isn't in every home yet, but it's getting closer. The pioneers are paving the way for a cooler, cleaner future. Magnetic cooling isn't the only alternative to vapor compression. Other caloric technologies use different forces to create cooling cycles. Elastocaloric cooling uses mechanical stress, stretching shape memory alloys to heat and cool them. Electrocaloric cooling uses electric fields to align and relax special materials, causing temperature changes. Each technology has strengths and weaknesses. Elastocalorics face mechanical fatigue. Electrocalorics require high voltages. Magnetocaloric cooling's advantage is non-contact force, less wear and safer than high voltage. The main drawback is the cost and weight of strong magnets. The future may see a mix of these technologies, each suited to different needs. From tiny electronics to industrial chillers, the race is on. The winner? Maybe not just one, but many. The goal: efficient, clean cooling for every application. The competition is heating up. We're on the brink of a new era in cooling. The old vapor compression cycle is no longer sustainable. Magnetic refrigeration offers a cleaner, safer path forward. The next step is discovering cheap, abundant, and durable magnetocaloric materials. Research is focused on common metals like iron and manganese. Engineering breakthroughs are needed for smaller, more affordable systems. Governments, companies, and consumers all have a role to play. With continued innovation, the magnetic fridge will become a reality. The move away from toxic gases is inevitable. The future of cooling is quiet, clean, and efficient. The magnetocaloric age is coming. Are you ready for the next cool revolution?